Ajay, am I audible?
Yes, sir, you are audible, sir.
How are you?
I am fine, sir.
So, how your PhD is going? I mean, you are on the submission stage?
Yes, sir. I am on the stage of pre-synopsis now.
Okay, so when your presentation is scheduled?
Sir, not in December. It will be scheduled in January only.
January only. Okay, so today
Yes, sir.
we'll be discussing the basic concepts of power and delay. Stay with us.
Sure, sir. Yes, sir.
Right?
Sure, sir. I am still. Yes, sir.
Thank you.
Welcome, sir.
Okay, so everyone, we will be starting with inverter. And as I told you before, that we'll be talking about the transient analysis, DC analysis, power, delay, how to make a symbol of inverter, everything today. And I would request everyone who is present over here to please download the Cadence or use the Cadence in your lab and start working on it, because watching someone doing the things is quite easy, but when you will start doing the things by your own, you will start facing the real challenges, right? So start doing it. It will be a great fun when you will be doing it, because when you get the troubles in doing the things in Cadence and when you resolve it yourself, actually that makes you a different personality as far as the VLSI is concerned. So I'll start with today's part. I'll open the terminal. No, it is not free, but I mean, if you talk about the Cadence, may I know your good name? I'm not getting your name, the one who has asked the question. Yes. So first, we will be starting with the point from where we stopped yesterday. I will be making an inverter first. New cell view. And cell view in which library? The library that we have established. Like yesterday I made the inverter 1. Today I'll be making inverter new schematic by the name of inverter 2. You please all see this very carefully, because I will not be repeating the concept of inverter again. And if you are willing to learn the concept of static memory, it is very important that you understand the concept of inverter. Now, I will press I for adding the instance. This is GPDK 45 nanometer, NMOS 1 volt, symbol, close, hide, and there you get NMOS. Similarly, again press I, browse, go for PMOS 1 volt, symbol, close, there you get PMOS 1 volt. Hide, place it here. Now you have got both of the MOSFETs. Now we have nothing to do with analog library. From the we have nothing to do with GPDK library. GPDK library is merely required for giving you this MOSFETs only. The rest, all things will be done by this analog library. Now you go to browse, go to analog library, start selecting the other things like you need VDC symbol. See, remember, always select the symbol, because if you will see, there are many options: AUCDL, AULVS, this is HSpice, HSpice-G, and the other options. But the option that works on the schematic of your Virtuoso is symbol, right? Otherwise, your simulation will not give you output and you will find some trouble. Let me give the DC voltage over here 0.7 volts. You can give any voltage from between 0.5 to 1 volt. I am giving 0.7 volt. You may give 0.8, 0.9, 1 volt, 0.6 as per your choice. And there you have this. I will use R to rotate and I'll place it somewhere here. Now I'll start using the wires. This is a wire, and this wire connects to VDC, and then this body is connected to source for PMOS, body is connected to source for NMOS. Yesterday I told you the reason why do we connect body with source, so that they should not make any PN junction diode within the MOSFET. Now I will connect both gates so that both gates have the similar input. Connect both drains. This will get one ground, and there you have input. For I will see ground in analog library. There we get ground G and D. I'll place it here, and your battery also requires a ground, right? Now on this side of your inverter, I will place a pulse. So how to find a pulse in analog library? You have the constant voltage source by the name of VDC that will give you DC voltage. You want the pulse voltage now, and for pulse you will use V pulse. This. Now in V pulse you have 0 to 0.7 volts that you have taken, and the period is 20 nanoseconds. And the pulse width is 10 nanosecond. I'll explain you this concept, why I'm taking period 20 nanosecond, pulse width 10 nanosecond. Let me explain it, why to postpone this thing. I'll explain you. Annulate. Yes. Now please see, I have a pulse of this shape. This is a complete pulse. This pulse has, this is the off time, and this is the on time. Now, when I say that I am taking the period 20 nanosecond, it means that this whole pulse starting from here to here is 20 nanosecond. When I say that my pulse width is 10 nanosecond, it means the on time is 10 nanosecond. If I say that my pulse width, see, if it is 10 nanosecond and the whole pulse is 20 nanosecond, it means this is also 10 nanosecond. If I say my pulse width is 15 nanoseconds, right? Sorry, my period is 15 nanosecond and my pulse width is 10 nanosecond. Then what will be this off time? Anyone? What will be this off time?
40.
How much? How much off time will be there? 5 nanosecond. Right. Very well said. Very well said. Okay. So I'll take one more example here. The example is that if I take the pulse period of again 20 nanosecond, this pulse period is 20 nanosecond, and I say that the pulse width is 7 nanoseconds. This pulse width is 7 nanosecond. It clearly means that the off time will be. So why I take it 10 nanosecond? So that I can have off time equal to on time. I hope you all got my point. Right? So I'll come back to the experiment. You please see. I have taken these things and I'll apply the pulse over here. And this battery requires the ground. And then I need the output of this. This wire cannot be open-ended. So I'll apply a pin over here with the name of out and direction output. This way. Till now, anyone with any doubts? I've created the structure. Any doubts in the mind of anyone? Okay, so it is clear. Now, when I use ADL for its analysis, what I will do is, initially, I will start with that which analysis I need to do. Let me say I need to do transient analysis. And I told you prior that when you do transient analysis, in transient analysis, you actually require the time domain in the x-axis. Should I explain how? I'll try to see if I can enumerate it. Yes. If I'm doing the transient analysis, it means that during transient analysis, I will be having the time in this part. Please remember, whatever analysis you are doing, you should be clear what you are doing. For example, when I show, whenever you draw any pulse in your notebooks, you actually take the time in x-axis. And what is this? This is voltage. So this is what the time domain is. When you are talking about the DC analysis, it means in x-axis you are having certain voltage. You can have anything in y-axis. It can be a voltage, it can be a current, it can be anything. But in DC analysis, in x-axis you will surely have a voltage, and in transient analysis on x-axis you will surely have the time, right? And it is you who is to decide how much time. Now let me explain you why. When you are doing when you are making this pulse, say I'll come over here, you have created a pulse with 20 nanosecond and the pulse width of 10 nanosecond. What does it mean? It means that there is a pulse which is having on time of 10 nanosecond and off time of 10 nanosecond, right? Now, if on time and off time is of 10 nanosecond, then your analysis should be more than of 20 nanoseconds. At least there should be one pulse in this. एक pulse होनी चाहिए ना, 20 nanosecond की एक pulse होगी. You should be having more than one pulse. So your transient analysis timing should be more than 20 nanoseconds. Whatever pulse you are taking, whatever time you are giving, your transient analysis time should be higher than what you are giving in input. Now I'll come back and launch the ADL. Where has gone the ADL? I'm not able to find it. Let me check. Yes, there you have the ADL. In this ADL, you will be doing the transient analysis. You select the transient analysis. This top time should be more than 20 nanoseconds, which incorporates a single pulse of 10 nanosecond off time, 10 nanosecond on time. So I'll take total time 100 nanosecond, which will incorporate 5 pulses. I can use it conservative accuracy, moderate accuracy, liberal accuracy, but I'll use conservative and I'll keep it enabled. Okay, right? Now I want to see the output, this output. Your ADL is now showing the output. But you should also compare it with the input, what input you have given. So there is no input. So you can give name to the wire also, in, and put it here. Now, in ADL, you can again go for output to be plotted, select on design, input. It has not picked up input. Let me check. Okay. Now it has shown gone input and output. Now you check which model file you are working with. It is 45 gpdk45.scs, right? Okay. Now run it. Let us analyze the results. This split current strip, this button will split your input and output. Now you please see it once. I'll select the annotations for yes, annotations for your clarity. Now you see, this is your red is your input. This red is your input, and the other color is your output. You see this input here, that every pulse has 10 nanosecond from 0 to 10 on time and 10 nanosecond off time. Similarly, 10 nanosecond on time and 10 nanosecond off time. And every time, whenever you give high, the output is low. Whenever input is low, the output is high. What is the meaning of high? What is the meaning of low? The meaning of high is this 700 millivolts, and meaning of low is 0 millivolt. Similar is here. From where this 700 and 0 millivolt has come over here, the concept has come from the pulse that you have given, right? So this is your basic inverter. In this, I want you to please note that if you slightly magnify this output, what you will notice here is that your input is at this point when it diminishes to 0, but your output is this point. and there is a gap between these 2 points. Can you notice this? That there is some gap. I'll magnify it a bit more. You please see. If you see this, it is ending up over here and it is rising over here. There is some gap. This is called the delay. Actually, what is the definition of delay? If you read the book of Neil Weste, it says that when your input is at 50%, means it is at 350, and your output is also at 50%, somewhere here, then the difference between the timing is the delay, right? So let us check that at this point, you see, it is 324 millivolts at 30 nanoseconds when it is coming from 1 to 0. But the pulse output is getting 0 to 1 at 320 millivolt is 30.197. The time is 30.197 for the output, and for the input time was 30.164. Means there is around 5 nanoseconds delay. The delay is of approximately, it is not 5 nanosecond, it is 0.5 nanosecond. Right? There is a gap between input and output. I'll tell you the process, how to calculate this precisely calculate this delay. I'll tell you this process today only. And with the exact process and with the exact explanation for that. Now, you have seen that inverter is working with the complete input and output. Now, what we'll do is, I'll close this ADL from here. It will say that whether you want to save the current state, I'll say yes. So it will save my current state with the state 1. Okay. So when I will open the state, it will start from here only. Right? So now what we will do is, we will create the symbol of this structure. I'm just willing to say that if someone is in list who want to join this meeting, yes, one person is there. Okay. Now we will create the symbol of this. For creating the symbol of any circuit, because you cannot use let us take example that if this circuit is having only 2 transistors, what will happen if any circuit is having 50 transistors and you want to make 100 copies of it? It will make it extremely confusing. So what we will do, we will create the symbol of this structure. Now, what is the process of creating the symbol? Please watch it very carefully. Remove all the voltage sources, all the grounds. I am going to create the symbol of inverter. You see that in your digital books, there is a symbol of inverter, how this is created in simulators. And create pins on all input and outputs. The direction is input, name is VIN. Put it here. Create a pin, direction is input, name with the name GND, ground. Place it here. Now another pin with the name VDD, place it here. Now your inverter is having 4 pins. 3 are the input pins, 1 is the output pin. Right? Now I will create the symbol of this inverter. To create the symbol, go to this create. There is cell view. From cell view, click. You will get this window. There is name of your library. There is name of your cell. Then what you are, from where you are making schematic, what you want to make symbol, and the tool is using, you are using a schematic symbol. Okay. Now you get this window. In this window, they want to know that in your symbol, where you want these pins. If we create the symbol of inverter, this is how inverter looks like. There you have in, and there you have out. Actually, here you have the VDD, and here you have ground. That is how an inverter actually looks like. So what we will do is, we will see that your VDD is on the top pin. So we'll cut the VDD from here and place it on top pin. Ground is on bottom pin. Cut the ground from bottom, from left pin, put it to bottom. Now your left pin is V in, it is already there, and right pin is out. Right? So your pin structure is now clear according to your structure. Now you click OK. This is what you see. Now you need to create a symbol. How you will create it? First of all, you will use delete this outer boundary. Delete the instance name and delete the outer boundary of this also. Right? Now you have, see, you have many shapes here, like you have in MS Word. Pick this and start making a structure. You have one line here. Your second line here and third line here. Right? Now, in inverter, you also have a circle in front of it. Take the circle, select it and move it to its front side. Just that I want to make it more clearer. That is why I'm not accepting it. This. And now move. This is your symbol. Now this symbol should have a few pins. Push this here to output. And connect this output with this symbol. This way. Now push this VDD to here. And connect it with Yes. Now push this ground from here. This way. And you can put your pin like this. This has not been connected properly. I'll connect it again. This way. And now this is your V in. So your inverter symbol is ready. This part name, press Q over here, name it INV and place it here. Now you can delete rest lines. So your symbol of inverter is ready. What you can do is now you can slightly improve these lines so that it can look better. This is VDD, this is ground. Okay. So because the time of this particular this Zoom meet is now over. So I would request everyone to please leave this meeting and connect with the same link again. Please connect with the same link again. And we'll start from here. We'll start using this symbol immediately.